Let us get started then. So, hello everyone, welcome to the 8th session of our OpenMP program. So far in previous session, what we saw was different scoping clause, right? So we saw what is first private, last private, and how to use them, where to use them with examples, right? And yeah, we also saw something called as thread private, which will retain the copy of variables as well as its value across all the parallel regions. And then we saw something called as copying, which will be used to copy the values from master thread to all other threads in case of thread private. Later towards the end, we were here, right? Sorry. So we were here, right? We were looking into copy private. So we saw this, right? That it can be used with, I mean, it is used with single clause and basically copy private will ensure that the particular variable that we are specifying in the copy private clause will be copied back to all other threads other than the thread which is executing the single. And we saw the example as well, right? So uh, yeah, so so this is what is the summary of the previous session that we saw. Now in the today's session, we'll be looking into few other directives and clause, like few other clause related to scheduling of the loops, and as well as the section directive and section directive will be looking into, as well as some runtime libraries will be looking into. So with this, let us get started. So yeah, so now let us see the schedule clause. So um, so far we have seen this thing, right? So let me share this thing, my whiteboard. So yeah. I hope that you're able to see the whiteboard now. So yeah, so far we saw this, right? That we can let me go over here. We saw this thing that using hash pragma OMP parallel for followed by a for loop, whichever follows that this clause parallel for clause will be parallelized by the OpenMP. So essentially what will happen is that this parallel for is a work sharing construct here. So what will happen is that the iterations of this loop uh, will be divided among the threads. So let's say there are 10 threads and number of iterations are 100 and we have 10 threads, right? Then each thread will get 10 100 by 10, which is uh, 10 iterations of this loop. And the way the scheduling happens is quite simple, right? We saw this, like the way the scheduling happens is that thread 1 will get 10 threads, that is from 0 to 9. Thread 2 will get another chunk of 10 threads, which is from 10 to 19, and so on. Thread 10 will get 90 to 99, right? So this is the way the allocation is done for this case, hash pragma parallel for. Now, this might not be the optimal way. I mean, this might not be the optimal way to distribute the work the way we are doing it here, right? The way we are doing it here, this might not be the optimal way. So to highlight on this point, let us consider an example here. So let us say that your loop is your loop looks something like this, right? So let us say that you have loop like this. So you have something like this. and within this loop you have another for loop, right? And j equals to 0, j less than I, j plus plus, right? You might have something like this also. Now in this case, let us say that you are parallelizing the outermost for loop, which is this one. Now, what might end up happening here in this case is when you add hash pragma, right? OMP parallel for, what OpenMP will do is that it will uh, divide this iteration of this outermost loop, iterations of this outermost loop into among the n threads, so not n threads. Here n is the number of iterations. So let us say that m is the number of threads here. Then it will divide n iterations among m threads. And what will happen is that each thread will get the consecutive chunk of the iterations. But this might be the issue here, right? Because if you see here, the within the innermost, within the inner loop of this outermost loop, the number of iterations in this inner loop are proportional to I, right? So for let's say for iteration number 0, the number of iterations for this inner loop will be 0. For first iteration, it is 1. Second iteration, it is 2, and so on, right? So here, amount of work is proportional to the size of I, right? So what might end up happening in the way we schedule, as we saw here, right? This way of scheduling, right? That first 10 threads are assigned to first, first 10 iterations are assigned to first thread, and second 10 iterations are assigned to second thread, and so on. What issue can happen here is that the let us say that again n was 100, and let's say 10 m equals to 10. Then assigning first 10 iteration to thread 0 and last 10 to thread 9 will lead to unequal amount of work being distributed among the threads, right? Because this I is proportional to, sorry, this inner loop is proportional to I, right? So the last 10 iterations, might be much larger than the first 10 iterations. I mean, the amount of work that you do in last 10 iterations must be much larger than the first 10, because for last 10 iterations, I will be much larger, right? So inner loop will run more times than the than this case, right? For here, for this case. So I hope this is clear. So just to make it more visual, yeah, let me do this. So to make it more visual here, this is the case, right? So this is the first iteration. It's the amount of work that we do in first iteration. It's the amount of work we do in second iteration. It's the amount of work we do in third iteration, and so on. So this keeps on increasing. For the last iteration, the amount of work we do is huge, right? So here, doing this kind of scheduling, we're assigning first two iterations to thread 0 and this to thread 1 and so on. Thread 10 here, or M, let me say M here, is not an optimal way to distribute the work, right? So yeah, so I hope this point is clear. So distribution of work among the distribution of iteration or work among the threads is a challenge here. So we need to make sure that we need to distribute the work among the threads in almost in equal proportion. So there should be some balancing that needs to be done here. And this is where this schedule clause comes into the picture. So what schedule clause allows us to do is that it will allow us to do some scheduling with the distribution of the iteration or the work among the threads. So if we don't mention anything, then OpenMP will do its default scheduling, which is this, right? Assigning like this. But using the schedule clause, you have some degree of freedom to allocate the iterations among the threads. So let us look into this now. So let me share my slides again. Right. So this is what I was talking about so far. That parallel for does equal distribution of iterations for all the threads, and yeah, in general, if you have n iterations and n iterations in the loop and p threads, then n by p iterations are assigned to each thread, and that might not be the optimal way to distribute the work, as we saw in that example, right, in the whiteboard. So we might need a different distribution mechanism, and this is where the schedule clause comes in, and that allows us to specify how iterations of the associated loops are divided among the threads. So in general, it is like very convenient to, I mean, using schedule clause is convenient way to work with loops, because it will allow us to majorly distribute the work properly. So let us look into this now in a bit detail. So, okay, yeah. So coming to schedule clause, its syntax is simple. We'll write this hash pragma OMP parallel for. This part we already know, right? This thing we are already aware about. Hash pragma OMP parallel for, followed by sorry, followed by this clause, which is schedule clause, and then we'll specify two other arguments to it, which is type and chunk size. So what type says is that what type of schedule do we want, or what, or how do we want to make the assignment among the assignment of iterations among the threads. So that is what is governed by type. And second thing is this chunk size. So what chunk size tells us is that how many continuous set of iterations do you want to assign to a particular thread. So if you, I mean, this is an optional parameter. If you don't specify it, then OpenMP will by default do its own create its own chunk size. But yeah, you can also specify your own chunk size, and we'll look into how we can specify different chunk sizes and see the behavior. So this is clear, right? The one is type of assignment and second is chunk size. And yeah, this is the syntax where we are using hash pragma OMP parallel for, followed by schedule, and then specifying type and chunk size. Now coming to type, so chunk size is nothing but an integer, right? So it is a positive integer, to be more specific, because you can't specify the negative chunk size. So chunk size must be positive integer. Coming to type, we'll be discussing three main types here. One is static type of scheduling, another is dynamic type of scheduling, and third is guided type of scheduling. Okay, yeah, so far so good, right? Any questions up till now? Anyone having any questions? Let me quickly see the chat. Okay, if there are no questions, then let us move ahead. Okay, so coming to the static schedule, which is the first one here. So static schedule is quite simple. What we'll do in static schedule is that when we, okay, coming back to the syntax here, hash pragma OMP parallel for schedule followed by type, which is static here in this case. So in type section, we will now specify the static, which will say, which will say to OpenMP that we want to use this static schedule for the assignment of the work for this loop. So coming to this static schedule, the way it will make the assignment is simple. So it will go in a round robin manner, and will do the distribution of work in that way. So I hope that you know what is round robin manner, but even if you don't know, that's fine. We'll look into this example. So let us consider this example. So we have this loop, right, in which we have 10 iterations. So here I have specified ITR, which is the iterations which goes from 0 to 9. And let us say that you have either two, we'll take both this scenario with 2 threads and 4 threads. And let us say that you have specified the scheduling as hash pragma OMP parallel for followed by schedule and then static comma 1. So type is static. One is the chunk size. Chunk size is 1. So now let us look into, let us go back to the whiteboard to understand this example pattern. So yeah, so let us look into this. So okay, yeah, so we have 10 iterations, right? From 0 to 9 as we saw, right? And let us say that we have two threads here, t equals to 2. And yeah, and what we specified was static comma 1. So static schedule will make the assignment or will distribute the loop iterations in the round robin manner. So what will happen is that we have two threads. So thread 1 will pick up this one. Okay. Thread 1 will pick up this 0, 2, 4, 6, 8. And what will happen to thread 1 is that it will pick up this 1, 3, 5, 7, and 9. So this will what will happen when we specify t equals to 2. So there are two threads. One is this one, which is specified by green here, and another is the red one. So thread 0 will pick up all this iteration, basically even numbers and even number of iteration, the iteration which where I is even, and thread 1 will pick up where I is odd, right? So this is how the scheduling will happen. So, okay, so this is fine. Now, let us say that you do this thing, right? So, let us say that you have 4 threads instead of 2 threads. And again, this is the same, static and 1. So now again, what will happen? So now the scheduling will be quite different. I mean, the way the iterations will be divided among the threads will be quite different. So now what will happen is that thread 0 will pick up 0, 4, and then 8. Yeah. Thread 1 will pick up this 1, 5, 9. Thread 2 will pick up 2, 6, right? And thread 3 will pick up 3, 7. So I hope you are getting this. So each thread is picking up the iterations in the round robin manner. So thread 0 picked up 0. Then thread 1 picked up 1, thread 2 picked up 2, thread 3 picked up 3. Then again, we came back to thread 0, which picked up the 4th iteration. Then again, thread 1 came in and it picked up the 5th. Thread 2 came in, it picked up the 6th, and thread 3 came up and it picked up the 7th. So yeah, I hope you got a bit of idea about how the scheduling is happening in case of static. Now, let us do a different exercise here. So let us say that instead of this, you say static, and then you specify 2, right? And again, number of threads are 4, right? So now in this case, how will the scheduling happen? Again, let me use a different numbers. Let me write this now. So yeah, so here to note that here we have chunk size as 2. So sorry. So what will happen here is that each thread will pick up 2 consecutive iterations instead of 1. So here we were each thread was just picking 1, and it was then waiting for its turn to come back, which was happening here, right? Thread 0's turn was coming back here, and then it was again picking up 1 iteration. So now what will happen is that chunk size is 2, so each thread will pick up 2 iterations. So uh, thread 1 will pick up this 2, then thread 2 will pick up this 2, thread 3 will pick up these 2, and thread 4 will pick up these 2. And then again, it's turn for the, I mean, it's now again thread 1's turn. So it will pick up these 2, right? So I hope this is clear. Any questions up till now based on what we discussed, like how the scheduling is happening for this case, static? Any questions? Okay, if there are no questions, then if you can observe here, there is one minor issue with this, not minor issue, but one thing you should observe here. The thing is that even after making this assignment in round robin manner, what might end up happening is that one thread might still be overloaded. So in this case, if you see, this is assigned to thread 0, again, this is assigned to thread 0. So here we have 4 threads, T0, T1, T2, and T3. And if you see, each thread is getting just 2 iterations, except T0, which is getting 4 iterations. So if you see here, there is some amount of load imbalance that is still, load or the disparity in the amount of work that is being assigned still happening here, which is for T0. So this can be even worse. Let's say you specified chunk size as even larger number. Then in that case, and let's say that last chunk fell into thread zero's pocket. Then in that case, again, there might be a lot of imbalance in the amount of iterations or the works that are assigned to the one particular thread. And just to note here one more point, we are assuming that not number of iterations, but the amount of work within each iteration, right? So these are all the iterations. The amount of work within each iteration are amount of work is almost the same, but that might not be the case, right? As we saw in this one. Okay, let me go back. So as we saw in this example, right? This one, yeah, here amount of work might not be same for each iteration. So even we are not considering that case. So yeah, still there can be some imbalance of the amount of work that each thread does, but in general, it is better than better than specifying no schedule at all. For the case where you can, for this case, you can even get some level of load balancing done when you specify the iterations in the round robin. You divide the work in round robin manner. Any questions so far? If there are no questions, then let us move back to our slides. Okay, so as I explained for static schedule, the assignment is made in a round robin manner, and we went through this example as well, right? For different chunk size and yeah, a different number of threads. And yeah, as we saw, there can be still some possibility that a particular thread might still be overloaded or underloaded with this type of schedule. And yeah, even we saw this, right? Each iterations might have a different amount of work. In that case, again, there can be some overloading, or one particular thread can be overloaded or underloaded. So far, if so far we are clear, then let us look into this example program. Okay, so yeah, so let us look into this program. So this is the program that demonstrates the static scheduling. And if you see here, there are 2 iterations. First one is this one, and the second one is this iteration. Each of them are going from 0 to 19. And what we are doing here is that in first case, we are just specifying hash pragma OMP parallel for, and in the second case, we are using hash pragma OMP parallel for schedule with static scheduling and chunk sizes too. Now, I want to ask each and every one of you, what will be the output of this program? Or rather some explanation around how can you, how will you be visualizing, or how will you be thinking about the work division that will be happening for this iteration, I'll wait here for a few seconds and then we'll discuss about it. But please try offline, like try how will the distribution of the iterations of this loop will happen in this case and this case. And in general, what will be the output for both of these printfs? Okay, anyone would like to comment? How will the output look, or how will be the distribution of iterations?
I guess in the first for loop, it's random. Suppose if we have 4 threads, then
Mhm.
the threads will pick up randomly. We cannot guess, it can be different numbers each time. But in the second case, as we mentioned, it is a static one. Each thread will be given the size of 2. Say 0, I, for I value 0 and 1, the first thread will pick up, and 2 and 3 will take the second. Suppose if there are 4 threads, then it will be equally distributed among 20 values.
Okay, so in first case, you are trying to say that randomly the iterations will be distributed. That is what, right?
Yes.
Okay, any specific answers like how will the distribution look like? For both the case, I think there can be some amount of determinism that we can add to our answers for at least for this schedule is what I'm thinking. Uh, Anyone who would like to comment?
Maybe in the first for loop, 4 by 4, 1 by 1, say for I0, thread 1, thread 0, I1, maybe some thread for 3. Then once the for first 4 values of I, 4 threads are allocated, then it will take on the next 4 threads. I don't know, I'm just guessing.
Okay. Yeah, fine, that's fine. Anyone else would like to add? Okay, that's fine. So yeah, so let us look into this one. So what will happen here is that um, as we saw, right, when we specify nothing, right, with this hash pragma and the parallel for, what will happen is that uh, each uh, each thread will be given the iterations and iterations in a particular chunk, and each thread will get, let's say, here in this case there are 4 threads, right? Because I haven't specified the number of threads here, and my system has 4 cores, so by default it will take I think 4 threads, which should be the case. Uh, and there are 20 iterations, right? So what will happen is that each thread will get 5 iterations. Now you should be clear here that how these iterations will be assigned, and that is also quite deterministic here in this case. Thread 0 will get T0 will get sorry, these 0 to 4. T1 will get 5 to 9. I think, yeah, 5 to 9, and so on, right? So this is how the distribution is done in this case when you specify nothing, and we'll see with the output as well. And the second case is hash pragma in parallel for with static scheduling with 2s chunk size. So in this case also, as we discussed, thread 0 will take 0 comma 1, then it will wait again for its turn to come back. So 2 3 will be assigned to some first thread, 3 4 5 will be assigned to second thread, 6 7 will be assigned to third thread, then again it will pick up 8 and 9, and so on, right? This is what will happen. And again for thread 1 it will be 2 3 10 11 and so on, and you can even go further for thread 3 and thread 2 and thread 3, how the assignment will happen. So any questions so far? Let me quickly show the output as well for this program so that we can confirm our understanding here that we saw here and here. Let me share my code screen as well as, no, let me share my console. Let us do this G++ minus F open static CP. Right? And once it gets compiled, let us do dot slash. Okay, so this is the output. So as we discussed, right, in the first case, it is printing nothing but I mean, not printing, but first thread is taking, which is thread 0 is taking 0 to 4, thread 1 is taking 5 to 9, thread 3, thread 2 is taking 10 to 14, and uh, thread 4 is taking 15 to 19. And this will be the same type of scheduling. I mean, this won't change even if you run it 100 times or 1,000 times. Same schedule will happen, same type of scheduling will happen if you specify the hash pragma of the parallel for. Right, so this is the first case. Second case is the case where we specified some schedule from R, that is using static clause. So in that case, how the scheduling will happen? So we saw this, right? Thread 0 will take 0, 1, then it should take 8, 9, right? So it took 8, 9, and then again it will wait for its turn and it will take some few more iterations. So in this case, I think nothing more, because by the end of this 8, 9, I mean, by the end of the next round, there might be no iterations that are left. But yeah, again, coming back to thread 1, it will take 2, 3, then 10, 11, then it took 18, 19, and so on, right? So this is coherent with what we saw right here. Let me share that back. Right, we saw this 0, 1, 8, 9, 2, 3, 10, 11, right? So coming back again to this. So this is how the scheduling will happen. And let me run it 2, 3 more times to see, like, this is coherent, right? 0, 1, 8, 9. And I think these are the trailing iterations that are assigned to some based on the availability, they are assigned to some threads. But if you see, 0, 1, 8, 9 are always assigned to thread 0. Then for thread 1, 2, 3, 10, 11 are always assigned to thread 1. Similarly, for thread 3, 4, 5, 12, 12, 13, these iterations are always assigned to thread 2, and so on for thread 3. For thread 3, 6, 7, 6, 7, 14, 15 are always assigned to thread 3. This is true no matter how many times you run. And similarly for this case also, right? We saw that thread 0, 0 to 4 will be assigned to it. Thread 1, 5 to 9, thread 2, 10 to 14, and thread 3, 15 to 19. So there is some amount of determinism. That was what I was trying to say in the way the work is distributed among the threads. I mean, the way the iterations are distributed among the threads. Sorry. So far so clear, right? Any questions up till now? Anything that was unclear here? Please let me know if there is anything that was unclear. Else we can move ahead. Okay. I'm assuming that this part is clear. Then let us move ahead with dynamic schedule. So yeah, so far we saw that this thing, right? Let me go back to my whiteboard. That even after using the static schedule, as you can see here, there can be some work imbalance or the load imbalancing that can happen among the threads and by not distributing the work properly, even if we use the static schedule. So to mitigate this drawback, or to reduce the this drawback, reduce this load imbalancing that is happening here, we I mean, OpenMP came up with this dynamic schedule. So in dynamic schedule, what will happen is that the iterations will be distributed among threads based on the availability. I mean, based on the thread's availability. So let's say thread is done with the amount of work that is given to then OpenMP will give some more amount of work to it. So that is how the dynamic scheduling works. So basically, dynamic scheduling allows the assignment of work in dynamic way. So as I said, right? So let us say that thread 0 was given, let's say 4 iterations, and it is done with those 4 iterations. And meanwhile, thread 1 is busy with some iterations, and there is still more work. Then what OpenMP will do is it will assign the some more iterations to that thread 0. So that is how the dynamic work is assigned in the dynamic way. And yeah, so this comes up because assigning the work in static manner is quite difficult, right? You can't predict at runtime that which iteration is time consuming, which is not, right? So based on the availability, based on the availability of a particular thread, the work is assigned to it. Okay, so let us look into this with an example, which is given here. So let us say that we have this, again, schedule clause with dynamic type, and one as the chunk size. And we have these kind of iterations. So iteration 1 has, so in this curly braces, we have specified the amount of work each iteration has to do. So iteration 0 has 3 amount of work to do. So larger the number, more the amount of work it has to do here. Thread 1 has 4, iteration 0 has 3, iteration 1 has 4, iteration 2 has 5, iteration 3 has 6, and so on, right? It is given based on what is given here. And we have 2 threads here. So let us see how the distribution might look like here in the dynamic case. So this might vary, right? The distribution might be quite different on each run for this case, because it depends on how early the thread is able to finish, right? But a hypothetical scenario, let us pick up this scenario itself, and let us try to understand how the distribution might look, right? So let me go back here and let me put this out again. So yeah, so we had this kind of thing, right? Iteration 0 was having 3, iteration 1 was having 4, 2, 5, 3, 6. Then 4 was again, I think, 4, 5 was 3, 6 was 2, and 7 was 1, right? Let us keep it till 7 only. So these are the iterations. Now, the scheduling that we have is dynamic with 1 as the chunk size, right? And let's say number of threads, we are just having 2 threads here. Now what will happen is that we have 2 threads, T0, T1. Now work is being assigned in dynamic way. So what will happen is that this iteration 0 will be assigned to thread 0. So it will do this thing from 0 to 3. Iteration 1 will be assigned to thread 1 since thread 0 is already busy executing. So thread 1 will get this chunk 0 to 4. Now again, after this time, the thread 1 is, thread 0 is idle, but thread 1 is still busy with its iterations. So what OpenMP will do is that it will assign this iteration 2 to thread 0. And again, at point 4, this thread 1 is idle. So again, in dynamic manner, it will, since this is idle, the OpenMP in dynamic manner will assign this another set of iterations to this one right here, right? So this will happen, and later, again at, so this should be it actually. So this is 8, right? After this time, again, this thread 0 is idle. So this one will be assigned to thread 0, which is 12. I think just see. So yeah. So this one. Then again, at this time, both of them are idle. So what OpenMP will do is that it will assign, let's say, this 5th iteration here, and sixth iteration here, right? And again, at this time, at 14th time unit, let us say, this thread one was idle. So this last iteration will be assigned to again thread one. Oh, sorry, yeah, thread one. And yeah, with this, if you can see, there is the scheduling of work is being done in a dynamic manner, right? So the main point here is that when thread is idle, it is assigned some work. So that is how this dynamic type works in this schedule clause. So based on the availability of the thread, the work is assigned to the thread. So now let us move back to the slides. If I'm missing anything, let me check. Right, so this is what we saw, right? The optimal way of distribution, iteration distribution can be difficult because we might not know what the amount of work each iteration has to do. So what dynamic schedule tries to do is that it tries to assign the work in a dynamic manner. And yeah, we saw this example as well, right? For two threads and this set of iterations, that how the scheduling is being done in dynamic manner. Any questions? Anything that was unclear?
This is basically round robin, right? There can be still better way of scheduling, like shortest job first, the conventional.
No, so sorry, but if I missed you, but so round robin was this one, static schedule. If you see here,
No, what I meant by round robin is that all the jobs, let us say this iteration 0, 1, 2, 3, all these iterations, let us consider them as jobs to be executed. They may be waiting in a queue. Let us assume that they're all waiting in the queue. In a conventional operating system, jobs will be picked up from the waiting queues and assigned to the processors based on round robin or something like that. This is basically, let us assume all these iterations are jobs, right? So the total time that is being taken is 15 seconds, 15 units of time. If it can be given in a better way, that can be, still we can reduce the time. That is what I'm saying.
yeah. So in case of dynamic schedule, if it can be done in a better way than a round robin, then it has to be done based on the scheduling, right? Here, because in round robin, as we saw,
Otherwise, how we
yeah.
are picking up these jobs from here in a round robin fashion, right? I mean, in a sequential fashion, right? The jobs are picked up from this queue only in a sequential way. Suppose if there are two threads, the zeroth iteration is assigned to the first thread, then first iteration is assigned to the second thread. Once it is done, then it is picking up the next available iteration, right? Instead,
Yes.
if we pick it up in a more dynamic way based on the amount of work to be carried out, I think still we can reduce this time. Is there any way to do that?
So if I got your question correctly, then you are trying to say that let us say that each iteration is of equal amount. Then in that case, yes, you are correct that it will be in a round robin manner mostly. Still, you can't predict, right, that which thread will finish first because each thread with same amount of work might also take different time because they are executing asynchronously. So that is the first part. Yeah, it can be a round robin. It cannot be a round robin. We don't for dynamic schedule at least. For static, we are sure. So that is the answer to your first part. Now coming to second part, can it be done in a better manner? So that depends, right? So in dynamic case also, it might happen that one huge iteration. Let us say that this third iteration was not 6, it was 1,000. In that case, whosoever, whichever thread that might pick up this third iteration might be the one who will be the last one to finish, right? Because this is the huge one compared to others. And in that case, it might still not be the appropriate one, appropriate scheduling that can happen. But since so issue here is that when you do this hash pragma MP parallel for followed by anything, right? Schedule or anything, right? Whatever scheduling you pick up, that is what I'm trying to say. what will happen is that it will assign a particular iteration to a particular thread only. So that is the issue. So let us say that there was a particular iteration which was having huge work that was to be done, and others were having very less work. And in that case, it will be difficult. I mean, uh, you need to write a code in such a way that you figure out that iteration and divide the work accordingly. So that is what I'll say. But yeah, did I answered or something was? Do you feel like something was missing?
Yeah, okay. Now I understand. Maybe in a real-time scenario, there'll be more number of the threads. We are talking about GPUs and other things. I mean, number of core processors. Maybe we'll have more number of processors so that this problem can be solved. Suppose
Yeah,
in this
maybe.
case, we have 8 iterations. Suppose what if we have 8 threads, then we can do it in all of them can be executed in a parallel way, right? I think.
Yeah, yeah, that can be the case. But yeah, so as a summary, what I'll say is that thing you have to remember is that whenever a thread is idle, it will be given some work, is what is ensured here in dynamic schedule. Yeah, but in general, there can be more threads and more complex scenarios, right? Based on your application that you are working with. And you need to see your application and understand which scheduling can be better for, which can be a better fit for your application. Okay.
Yeah.
Yeah.
So,
Any questions?
just to make sure that I'm understanding this correctly, so in the case of dynamic scheduling, the scheduling does happen in a sequential manner, but in a greedy approach, right?
Yeah, you can. Yeah, you can say that in a greedy approach it happens. Yeah.
So it's not possible that, for example, in this case, suppose the fifth iteration is taking the 3 units of time. So to optimize that, it's not going to do 6 and 7 on thread 2, right? It's only going to assign
Six.
6 on the thread that's free.
Yes. Yeah. So it will
Oh,
only assign 6 to the thread that is free. So it will ensure that this do not. We will see this with the example as well. So what it will ensure in most the cases is that these two iterations, right, 2 and 3, which are having maximum work, those are not assigned to one particular thread. So that is what is being ensured in most of the cases. But again, it depends upon the availability of the thread. But yeah, why I'm saying in most of the cases, because thread with larger work will always take more time, right, to finish. So, and similarly for this too, they won't be in most of the cases together. But yeah, we'll see.
oh, okay. So, and another doubt that I have, sir, is that in a for loop, the execution of commands is going to be similar for all iterations, right? So, on what basis is this weight assigned to iterations in dynamic scheduling?
Yes, so that is a good question, but yeah, I think we already discussed this part. Let me go back to hmm. So we saw this slide, right? So this not slide, this thing, right? There can be a piece of code that you want to parallelize, which might look something like this, where there is the outer for loop, which is going from 0 to n, and then there is this inner for loop, which is going from 0 to I, and you want to parallelize the outer for loop. In that case, each iteration of the outer for loop might have the different amount of work to do. So iteration 0 might have 0 units of work. Iteration 1 might have 1 unit of work. Iteration n might have n units of work to do, right? So that is what I was trying to say, that here, if I go back to slides, it can happen, right? It can happen that each iteration might have uneven amount of work. So from the example that we saw in the whiteboard, right? It was one iteration 0 was having 0, iteration 1 was having 1, and so on. But yeah, this might well be the case, right? We can hypothetically engineer a code where this might be the case, which we'll be seeing in the next code example as well. in general, your application might also encounter such scenarios, is what I'm trying to say.
Okay, so thank you.
Okay, any other questions? Okay, if there are no questions, then let us look into the code. Right, so this is what I was talking about. So what I've done here in this code is that instead of making 5, 6, 7, 4, 3, 2, 1, I've done this thing 50,000, 60,000 to just make sure that the iterations are large enough so that waiting time is good enough for each thread. So what I've done is simple. I've written a outermost for loop here with 8 iterations, and then the innermost for loop, where innermost for loop is based on, I mean, the number of iterations in the innermost for loop is based on this ARR of 5. So this one, if you look at this code, this is very similar to this what we saw here, right? Let me go back. Right, very similar to what we saw here, right? Each iteration, there are 8 iterations as we saw in the code. Here there are again 8 iterations, and each iteration have different amount of work. Similar to, let me go back. Similar to what we are seeing here, right? So there are such, this is the for loop 1, and this is the for loop 2. So there are 2 such iterations. I mean, there are 2 such loop, not iterations, 2 such loops. Here in this case, we are having, and first loop, I mean, the first outermost loop, we are parallelizing this using #OpenMP parallel for, and second one using same parallel for, but scheduling is dynamic here. And yeah, we have already seen this example, worked out with this example, but now let us see how the scheduling is being done, right? So are we getting some benefit out of this? So if the scheduling was, I mean, not static, but if the scheduling was not specified here in this case, right, which is our first case here, what will end up happening is that this 2 expensive operations, right, this 2, which is 70,000 plus 80,000, that is 150,000 iterations will be assigned to thread 1, right? So this will go to thread 0, this will go to thread 0, this will be going to thread 1, thread 2, and thread 3. So thread 3 will have very little work, and thread 1 will have a lot of work to do. That is what will happen in this case. Now, what we want to see here is that by using dynamic scheduling, are we getting some benefit or not? So that is what I'm trying to illustrate by using this example. So let us look into this. Let us try running this code. So let me do this. Right, I compile this one. Now I'm doing right. So you can see in the serial portion, as we all know, right? Thread 0 will be assigned 0, 1. Thread 1 will be assigned 2, 3. Thread 2 will be assigned 4, 5. Yeah, and thread 3 will be assigning 6 and 7. So there is an issue here, right? I mean, not issue, but imbalancing of load imbalancing that is happening here, because iteration 2 and iteration 3 are the most costliest one, and they are being assigned to just one thread. So that should not be the case. But if you see here in this case, right, the 2 most costliest one should be to the different threads. So 2 is being assigned to thread 0, and 3 is being assigned to thread 2 here. And similarly for the most light ones, right? I mean, the last 2 iterations, if you remember, were the most light operations. I mean, very inexpensive ones, to name it. So those were 6 and 7. Those were being assigned to the same thread again here. And let us say if it is being done somewhat in a better manner here. So somehow again it is being assigned to thread 3 here only. But the point here to note is that still this is better than assigning in a static manner, right? Because the point here is that the iterations might be more balanced here based on the availability of the threads. So it will happen that the most expensive ones at least won't be assigned to the same thread, because the most expensive one will be the ones will take more time, right? So that is what is the idea here. Yeah, any questions or anything that was unclear, please feel free to ask. So this one was the dynamic scheduling. Okay, coming back to the slide. So third kind of schedule that we want to see here is that the guided schedule. So in case of guided schedule, the uh, amount of work that will be assigned to each thread will be halved with each assignment. So what essentially will happen here is that you will specify some chunk size, right? So the uh, uh, the quantum or the amount of work that is being given to each thread will be governed by this chunk size, and this quantum of work will be designed in such a way that it will be reduced. I mean, it will be reduced in each assignment. So let us put it in a better manner. So yeah, let us work with an example here. So let me go back. Um, so let me pull this out again. Right. So in case of guided kind of schedule, right? Let us say that you are using so this should be like this, right? Guided comma. Let's say you are using a chunk size of 8 for a guided kind of schedule. Right. Now, what might end up happening in this case is that the way the scheduling is being done is in the way of, I mean, is based on this chunk size. So what OpenMP will do here is that it will create okay, let me be more specific here. So let us say that number of iterations are somewhat, say let's say 130 iterations we have, and we have 4 threads, right? T equals to 4. Number of threads are 4. Now, what might end up happening in this case is that OpenMP makes the quantum, I mean, the amount of work that is to be given to each thread on each assignment based on this chunk size. So what it will do is that it will create a chunk size of 32, which is nothing but 8 into 4. It might create 2 such chunks. Then it might create a chunk of size 16, which is nothing but 8 into 2. So please note that this 8 is coming from the chunk size here, which is written here, right? And then it might make few more chunks of size 8 itself, right? And I think 32, 64, 96, right? And then yeah, then we are left with 2 iterations. So it will create again a smaller chunk of size 2. So this is just a leftover thing, right? All this should sum up to, all this entire thing should sum up to 130, which is our number of iterations, right? So it might what OpenMP might do here is that it will create a amount of work that needs to be assigned to each thread in such a way that it can half it each time, right? And the advantage here is that the amount of work is being halved in each assignment, and in that way it can, I mean, what OpenMP can ensure is that the amount of work will be almost equal. Yeah, so that is what is the guided schedule. Let us look into an example as well. Meanwhile, any questions, then please feel free to ask. Let me go back to the code here for the guided schedule. Again,
So I had a question about dynamic assignment.
yeah.
So is it possible for dynamic assignment to optimize our scheduling even if the the time units required by each iteration is dynamic? So, for example, in that example that you were talking, where you had an array which defined the iteration of, yeah, the inner loop on this one. So, suppose if in the second part of this, the second loop, what were to happen if after each iteration we were to modify the value of next array index based on the value of this iteration?
Hmm. So that is a good question. I think we can try this one. I even don't know the answer, so that's why I'm saying. Let us say that you are trying to modify this thing, right? But I don't think. Okay, let me try this. Let us do this, right? Let us see if it works or not. First of all. Hmm. Okay. Not here, but here, right? So here, what we are trying to do here is that we are trying to update this PR of I based on not based on, but we are trying to update it dynamically here, right? So let us see if this one works.
So this would not run,
Okay,
because
why?
j would be 0 for the first iteration, area would become 0, and the next iteration would not even run.
Okay,
So
yeah.
what I was
So
asking
we
is,
can,
for example, if we set array of I plus 1 based on j's value somehow, so the
yeah,
next iteration would be dynamic.
yeah, this can be done actually. This thing, right? You are talking about this one,
Yes, sir.
this thing, right? So here, zeroth iteration will set uh, the amount of iteration that I mean the amount of work that next iteration will do. That is what you are expecting, right? If I'm not
Yes, sir.
wrong
So
here.
there's dependency between each iteration.
Yeah, let us try this. Let us see if this one works. I'm hoping if there are no loop carried dependencies, not loop carried, but let us see if this works. I think it should, but let's. Okay, J was not declared in this scope because obviously it is not there here. So let us do this thing then. Let us do this, right? Let us keep it I only. So what will happen is that, or let us make it I plus 2, right? So what will happen is that each outermost iteration, what it is doing is that it is setting the amount of work that needs to be done for its next iteration, next outermost iteration. And that is being increased incrementally, right? So first outermost iteration will set some work for the second one, and this will keep on increasing. I mean, it will keep on increasing for each outermost iteration. So yeah, let us do this. Let us try compile this one. I think this should work, but let us see. Yeah, it is working. So essentially, it is based on the amount of work that each thread has and the way it is able to finish it. Okay, any questions?
Sir, but in this distribution, thread 3 seems to be getting most of the
Yeah,
load here.
yeah. So I think this is because of. I think this must be because of the way the threads might be ending up being free or something like that. We need to think through this, what actually is happening in this scenario. But essentially, if a particular thread is free, then that must be the one which is being assigned. Or if let's say all threads are free, then OpenMP might pick up random thread and might assign the work to it. So that might also be happening in this case. So that is what we need to look into the code and
So, sir,
understand
is
what.
it safe to assume that OpenMP can optimize even these conditions?
So highly depends, right? So in this case, let us pick up this case itself, right? So in this case, it ended up happening that it doesn't do it quite efficiently, right? So again, you need to look into the application. here in this case, we need to look and see how we can optimize it properly. So maybe in this case, right, it might be the case that the static schedule might be the better, or the guided one might be the better, but dynamic might not be. So you have to see uh, how the work is there for each iteration and what kind of scheduling can be better. So even I need to think through like what can be the better way for distributing the work in this case. But yeah, we can take this as a homework or something like that and see how we can do this in a better way.
Okay, got it. Thank you, sir.
Yeah, but in general, to answer your question, it seems like yeah, dynamic can even do in the case where the iterations are changing dynamically. The amount of work is changing dynamically. Okay. Any other questions?
Thus, guided means it somehow OpenMP can quantify the amount of work to be carried out, then assign the work. Is it like that? Guided means.
No. So yeah, that is what. Let us go back to the whiteboard again. So this is the issue, right? We are thinking that OpenMP is able to see the amount of work and it is able to. So that is not the case here, right? When we say 130 iterations and dividing the work like this, 32, 16, 16, what essentially is happening is that it is just dividing the iterations of the outermost loop. Within the iteration, it doesn't still know that what is the amount of work it needs to do. So here is where you as a developer, I mean, we as a developer needs to apply our brain. So as I was telling that, right? So what might happen here is that this chunk, right? This chunk or this piece of quantum of work, right? Might have some iteration which is very, very expensive, and uh, to whosoever thread this is assigned, it might end up getting in a overloaded.
No, my question is, first of all, how
Yeah.
we have decided about this 8 by 4, 8 by 4, 8 by 2, how it is being decided?
Yeah, that is being decided because each time the work that is being assigned is half. So uh, that is why these chunks are being created. That is how these chunks are
So
created.
guided is only that dividing the work off and then distributing.
Yeah, giving, I mean, reducing the amount of work each time. So that is what is the guided.
Okay.
So by the way, for guided, I don't have a very good example. I have a example, but that, I mean, when you will see that example, you won't get a
Then,
sense of why doing
yeah,
it
then in
guided.
that
But
case, for
yeah,
me, the scheduling, all the three scheduling types, they all in a way static, right? They are not very dynamic. Just now we have seen the dynamic also led into some scheduling where the scheduling was not proper. Last example you have seen.
yeah. So again, we need to see why that is happening. We just can't comment that it is not scheduling it in a proper manner. Again, as I said, right, it might happen that all threads might be idle, or it might happen that the threads, I mean, thread 3 was assigned a lot of work in that case because uh, I mean, we need to see the scenario, right? It might happen that that was the only thread available, or it might be the case that all of them were idle. So we just can't comment based on that thing. And it's not like it's a static, it's still a dynamic based on the availability of thread.
What I would say for dynamic is that, as I told you, if we know that the example where I talked about, no, the scheduling, the conventional operating system scheduling algorithms, there
Yeah.
we were able to do it, right? We can able to identify if in the waiting queue
Okay.
there's amount of work that is to be done. If we can do there, then why can't we do it here?
Yeah, that part I'm not sure why OpenMP doesn't do that, but let us say that yeah, so I understand what you're trying to say
That is
here, that
dynamic, right? This is not
yeah,
dynamic. In a way, it is static.
in that way, yeah, it's static. In that manner, if you're thinking in that manner, it's static, yeah. If you are so I understand your question. So what you are trying to say is that if we know the iterations and the amount of work that we need to do in uh, a prior manner, like then we can distribute it in such a way that it happens to be a very equal amount of work for each thread, right? That is what you are trying to say, right? That is what I'm understanding from what you are trying to
Yes.
say. Yeah, I think that is not happening in this case, at least as what we are seeing here. And even dynamic is not doing it in that way. But yeah, to summarize it, it is just based on the availability of the threads. What is for OpenMP, what dynamic is it assigns based on the availability. So that is what is dynamic for OpenMP. But if you are comparing with our operating system's dynamic thing, then yeah, it is not doing it in that manner. Okay, any questions? So this was a good discussion. Thanks. Any other questions? Okay, so by the way, what I spoke here, like let's say this was just an example. So it might happen that OpenMP just create one chunk of size 32 and then other chunks of size 8 and so on. It depends again on OpenMP how it does this creation of this amount of work that needs to be assigned, right? So again, I have an example for guided, but as I said, it's not a really very good example. But again, I just created it for the visual representation sake. So again, we have this for loop where we are using a normal parallel for without any scheduling. And again, here we have guided with the number of, sorry, chunk size as 4 and scheduling as guided. And we have this loop again with 50 iterations. And in both cases, what we are printing is the thread ID followed by the iteration number. And yeah, let us try running this one to understand what does it give us. Right, so this is what is the output. In serial case, we are like super sure, right? This will happen that 10 iterations will be assigned to one and then again and so on, right? In that fashion only. So n by n threads will be, sorry, n by n m n by m iterations will be assigned to one threads and then the second one and so on. So that is what is happening. So second one is the case for guided scheduling. So here what is happening is that, as we discussed, right, that there is one big chunk that is being created and that is being, I think, is being assigned to thread 3 here. And again, there is a smaller chunk, slightly smaller chunk that is being assigned to thread 2 and then thread 0 and then again thread 1 if you see here. Yeah, and then I think there are a few trailing ones that are being assigned to the thread 0, right? So that is how the assignment is being done here. So we picked up the chunk size as 4. So that the amount of work will be in the multiple of 4s, but in general, it can happen that it is not in the multiple of 4s because the number of iterations might not be divisible by 4, right? So this might even end up, this might, this case might even end up happening. Any questions? Sorry. So this is what is guided. Each time the amount of work is being assigned is being reduced. So that is what is the main idea behind the guided scheduling. Okay. Yeah, if there are no questions, then let me go back to the slides. Okay, I think we saw all these things. Amount of work that is being assigned is half each time during each assignment, and chunk size defines the smallest amount of iteration that are need to be grouped to form a single piece of work. the single quantum of work that we want to assign, right? So yeah, so far so good. If there are any questions, then please feel free to ask here, or yeah, else we'll move ahead here. So yeah, the next thing that I would like to discuss here is the sections directive. And again, coming back to this sections directive, it is again a work sharing construct like parallel for. And yeah, when I say work sharing construct, let me go back here to the whiteboard. Right, so we saw this, right? Parallel for, right? What it does is that it will share the work. I mean, not work, but it will share the number of iterations that are there in the loop that follows it in some fashion, and we can specify how we want to um, divide that iterations among thread using these schedule clause, right? So this is what we saw so far. One thing that I quickly want to highlight here is that we can also do this thing. So I have a code for it handy. So we can also do this thing, right? Think. Yeah. So we can also do this thing. So hash pragma MP parallel followed by hash pragma MP for. So what essentially will happen in this case is that this hash pragma MP parallel for is where the threads are being forked, and this hash pragma MP for is where the work sharing is being done, or the division of work, division of the work is being done. So okay, coming back to the whiteboard, what point I wanted to highlight here is that this hash pragma OMP parallel for is kind of a right. It's a kind of combination of both the things: parallel plus work sharing, right? So it's a parallel work sharing kind of a thing. This entire thing, and the point is that you can even break this. You can break this, right? You can write parallel here, hash pragma OMP parallel here, followed by for here, right? What I mean to say here is that hash pragma OMP for here, right? So what this part will ensure is that it will fork the threads here. No, not fork the threads, but yeah, it will create the threads here. So that is what is again forking. So it will fork the threads here, and by the time they reach here, all these threads reach here. Here we will divide the work, right? Divide the iterations. So as we saw in this example, right? So let me go back here. The forking will happen here, and work sharing will happen here. So I hope this point is clear. So this is what I wanted to highlight, because I think we haven't seen this kind of an example before. So I thought I should add this one before we start looking into these sections. So yeah, so this is what is one parallel followed by a for. But coming back to the sections, this sections is again a work sharing construct like parallel for. And what essentially it does is that it assigns different tasks to different threads. And to take an example here, so let us go back to our whiteboard again. Right. So in case of sections, what will happen is that you specify something like this: hash pragma OMP sections, and followed by that you have this region, and in this region, so by the way, this entire thing is inside a parallel some hash pragma OMP parallel, and within this, what you specify is that hash pragma OMP section, which is first section. Then you have again a second section, hash pragma OMP section, So this is second section, right? This is section 1, this is section 2. Now what this will ensure is that, let us say that there are 4 threads that are executing this section. What will be ensured here is that each section will be executed by one thread. So thread 0 will pick up this section, thread 1 will pick up the second section, and so on. So that is what is the sections. Now there might be a question here that let us say that number of sections are what happens if the number of sections are lesser than the number of threads, right? Which is the case here. We have just 2 sections and 4 threads. In that case, what will happen is that other threads will be idle. So 2 threads will be idle and 2 threads will be picking up these sections. And we cannot predict which thread will pick up which section here, but yeah, 2 threads will be idle in this case, and 2 of them will be working in this sections. And again, if the number of sections are greater than the number of threads, right? This was the another scenario. This was the first one. Another scenario is that, let us say that you have 5 sections and 4 threads, or let's say 8 sections. Let me put it in this way. Yeah, let us say that you have 7 sections and 4 threads. In that case, what will happen is that each thread will first pick up one section at least. So 4 threads, 4 section. Each thread will get to 1 section, and then rest 3 sections will be assigned to 3 other threads, and 1 thread might be idle in this case. So that is what will happen in this case, in case of sections. So again, it's a some kind of a task parallelism that we are doing here. So this is one chunk of work or one task that we want to do. This is the second task that we want to do here, and each task will be assigned to one particular thread, and that is what is being ensured by using sections. So it's a form of task parallelism that we are trying to achieve using sections. Let me go back to slides. Okay, so again, it's a work sharing construct because we are again dividing the work here. I mean, based on the sections, we are dividing the work, and yeah, each section is typically assigned to, I mean, not typically, it is always assigned to a different thread, and one thread will execute one section. So it's an type of task parallelism, and again, we saw this, right? Number of threads can be greater than or less than the number of sections, and in that case, either some of the threads will be idle or some of the threads will get multiple sections to execute. And yeah, this is the syntax. This is the syntax as we saw, right? Hash background be sections followed by clause, and then within this we'll have different sections. And please note that this entire thing is within the parallel region. So yeah. Let me see if I have an example. I think I will have. Yeah, so yeah, this is the example for it. So let me quickly explain this code. So in this code, what we are doing is that we have our main function in which we have this 4 arrays A, B, C, and D, and we are initializing the array A and B. And the way we are doing, I mean, implementing the task parallelism here is that we are creating sections here with no weight here. And what we are doing here is that within each section, we are doing some operation. So here we are adding 2 vectors or 2 arrays in this case, and assigning it to C, which is our third array. And in the second section, what we are doing is we are multiplying 2 vectors, basically multiplying each and every element of 2 vectors. And I mean, multiplying this vector A and vector B and assigning it to T. So this is how we have divided the work here among 2 different sections. So first section does the addition, second section does the multiplication. And yeah, and I think since I have not specified the number of threads here, so this will be again by default 4 threads, and we have 2 sections. So again, 2 threads will pick up 2 sections, and again 2 threads will be idle in this case. To improve the amount of parallelism, you can, amount of work that each thread does, you can, what you can do here is that you can even add more sections. Maybe you want to do something like this, right? Subtraction or something like this you want. Then you can do this also. And some thread will pick up this section as well, right? So what will end up happening if I run this program is that one thread will be idle for this scenario, right? One thread will be idle, 3 threads will pick up these 3 sections. So that is what is the expectation here. Now let us quickly try running this program, right? So let us do this. Right, so I think output is jumbled here, but so this is one thread 3 is executing one section, thread 0 is executing one, and thread 1 is executing one section. And in this case, thread 2 is idle. So the summary or the bottom line here is that each thread will pick up one section, and that will ensure the task parallelism here. So one thread will be assigned one section, and each thread will have some amount of work to do based on the section that is assigned to it. And this is how the task parallelism is achieved using sections. Yeah, I think we'll stop here maybe because we are on time here. But yeah, I'll wait here for questions. Maybe for 2-3 minutes. I'll wait here for any questions that you people have. Maybe I'll go back to slides. Okay, any questions? Looks like there are no questions. Okay, then just to summarize, what we saw today is just how we can apply scheduling within this parallel for or the for directive that we saw, and we saw a new directive today, which is sections directive. And yeah, I think that's it. So yeah, so in the next session, which is our tomorrow's session, what we'll see is that we'll see how to use few of the runtime libraries, and we'll see some of the applications related to the uh, OpenMP, and like in general what we have learned so far, how we can apply that thing using some real world or some applications. We'll see that in the tomorrow's session. Okay, with this, I think if there are no questions, then we can call it a day, and yeah, see you all tomorrow at 5 p.m. Until then, bye.